All right, Tanya, shall we get started?
That's great.
Okay, awesome. Hi, everyone. Thanks for being here. So a couple of announcements before we get started. The first is that the event is being recorded and it will be posted on the LLVM YouTube channel. And also, so we have quite a few slides to get through. So hold on to the questions until the end of the presentation. We'll have a lot of time there then to get through all of them. All right, with that, so Tess is here. Tess is our speaker for the event, for our March event. Tess has been working at the intersection of programming languages and GPUs for over 15 years. She's helped develop Brook GPU, one of the first languages for general purpose computing on GPUs. Tess received her PhD from Stanford, where she applied insights from programming language community to software development challenges of real-time graphics. She now leads the development of the Slang compiler project at Nvidia. I've had the good fortune of attending a couple of meetings with Tess in the last month, and I have to say that her enthusiasm is infectious. It got a lazy bum like me to go off and research shader combinatorics and other problems with current shader languages. So without further ado, here is Tess.
Hi, everybody. Yeah, so I'm Theresa Foley. You can call me Tess, and I'm going to be talking today about the process of taking the Slang shading language from research to production. But to kick off, I don't want to assume that everybody in attendance here is an expert in real-time graphics. I think we're going to have a lot of people who have maybe expertise in compilers or programming models and don't necessarily have a lot of familiarity with graphics. So I'm actually going to spend a lot of time today just kind of giving an overview of what real-time graphics programming is like and why there are interesting challenges there for language designers, compiler implementers, and generally people interested in tools broadly. Then I will talk about the Slang shading language and compiler, which is our particular contribution in that space, and give a little bit of an overview of what's in it before segueing into talking about our experience trying to use those tools and apply them to real problems at Nvidia. So to start with the top of this agenda, I want to start with the question of what is real-time computer graphics all about? And at the largest scale, it's really about simulating the shape and visual appearance of virtual objects, right? Which means simulating the physics of light in the context of complex and detailed virtual worlds. But no matter how much effort we put into real-time rendering on computers, we always kind of need to be respectful that the real world ends up being more complex than most rendering systems can be. So even something as tiny as this little beetle here with this rainbow iridescence pattern on its shell is something that most rendering systems would struggle to capture. And so we need to think that at the highest level, what we're doing when we want to do real-time graphics for games or anything like that is more or less trying to simulate photons in real time. And it's worth noting that all of us, even if we don't leave our house all that often, see an exceptional variety of visual phenomena each day. And all of those phenomena are based on the same fundamental physics of how photons interact with the material world. But the reality is that simulating those physics on even the fastest computers is just too expensive of a way to produce images, right? And especially in a world where real-time games and things like that want 4K resolutions at 60 frames per second, we end up needing some strategies that can make this problem tractable. And so I'm going to highlight two key insights that are really what makes real-time rendering possible on in the world today. The first of those is applying different approximations and models to these phenomena we see in the real world. And the second is utilizing specialized hardware like GPUs. And so I'm going to drill down on each of these a little bit, but to start with the first one, when we talk about building approximations or models, what we're really doing is building on the work of scientists who go out and study and taxonomize and model the real world, and then of computer graphics researchers and other computer scientists who then devise efficient algorithms that we can use to implement those models and handle specific cases of things that arise in the world. And so to get a little less abstract here and a little more concrete, we can think of this agenda of taxonomizing the way visual phenomena occur as thinking of broad categories of things. We can talk about the shapes of things we see. We can talk about how the shapes of fur differs from solid objects like rock. We can talk about how the movement of objects differs. And this tiger walking around is going to animate differently than perhaps the plants in the back swaying in the wind. We can talk about different materials, right? How the painted handle of this brush reflects light very differently than the metal on the tube of paint below or the marble. And then we can talk about light sources themselves, how lighting from the sun is very different in practice than the light we get from interior light bulbs. And so when we start to study each of these different components of how images are formed, we start being able to decompose the problem of forming images into thinking about these different categories of features. Now, the three I've put up on the slide here aren't the only ones, but there are ones that I think all of us can appreciate affect how images appear: shapes, material, and lighting. And given each of these categories of features that affect image formation, we can also understand that we can have many different implementations of these features based on different models that scientists or computer graphics researchers have devised. And so just a few of them on the slide here to show that for shapes, we might talk about static objects versus different kinds of animation. There's different kinds of materials that those surfaces can have or those objects can have. And we might use different algorithms to implement lighting for a directional source or a very distant source like the sun versus for interior lights like light bulbs. And so once we've taxonomized the world like this and come up with specialized implementations of different kinds of phenomena, now we can start asking the question of, it's also important to recognize that if we want to implement these on computer, we need to think about how these models, the scientific models, have different parameters that describe them, right? And that if we are going to make algorithmic implementations of them, they will also have these parameters. So the parameters that maybe describe how a metal surface varies its roughness or glossiness are going to be different from something like a translucent glass surface where we might need to know about its index of refraction. And so now we can take that kind of a taxonomization approach and look at the sort of what I would call the big picture of making a picture, how a real-time renderer is formed for somebody who doesn't write one for a living. So the big picture of real-time rendering, I'm going to divide into three big steps. And the first of those steps is that we need to build a large and extensible library of shader code containing many implementations of these different categories of features we've talked about. It needs to be large because we want to encompass a variety of different phenomena that occur in the real world, a lot of different kinds of materials and a lot of different kinds of animation and so forth. And it also needs to be extensible because our understanding of the world and the kinds of scenes we want to build are not fixed, right? We may come up with new algorithms and new techniques over time. And in practice, these can be quite large. That, if you look at something like a commercial engine like the Unreal Engine, we're talking tens of thousands of lines of code written in things like shading languages to express all the different materials and light sources and things like that the engine supports. The second step in this big picture view of rendering is that we want to be able to compose scenes with diverse kinds of objects in them. And each of those objects is going to pull together different features and different implementations of those features, along with values for all those parameters that those different models have. So if we imagine again our scene with this tiger in it, we may have a material that describes the fur of the tiger and some sort of texture image that describes how it varies in color spatially. But we may also have a material that describes the ground surface and a texture that describes its spatial variation. We might have different features that describe the skeletal animation of this tiger versus the animation of foliage swaying in the wind. And so pulling together all these different implementations of different features together in a single scene is our middle step. And finally, the third step of real-time rendering that we do over and over and over again. This is what we want to do every frame or for every operation within a frame. Often we talk about passes within a frame in the rendering world. What we're going to do is pick a program we'd like to use for that operation, figure out which objects in the scene are relevant for that operation, and then invoke that program passing whatever parameters we define for those objects into the program, which, I'm being very coy here about all the details, but this is the big picture of generating images. All right, and given this overview of the rendering problem and how it relates to these features and their different implementations, this is the time where probably people who are watching these slides and have any kind of background in things like object-oriented programming are going to be looking at my taxonomy and saying, couldn't we just take this taxonomy you drew, Tess, and turn it into a class hierarchy, just a base class for each of the categories of features and a little subclass for each of the different cases under them? And the answer here is that yes, you could do this. And in fact, this would kind of be literally a textbook approach if you're on CPU. So here we have an example of a textbook used often to teach graduate level computer graphics that uses exactly this kind of decomposition in order to be able to express a wide variety of rendering techniques. But the editions of the book that use this style primarily run on CPU and are not primarily oriented around performance. And that's where we need to turn our attention now to the second one of the criteria I talked about, or the insights that I talked about, that make real-time rendering tractable at all, which is the second piece of utilizing specialized hardware, which in practice means GPUs. And GPUs typically have things like fixed function texture filtering, rasterizers, ray tracing cores, and unique programming models, and all kinds of other considerations. And so the second problem we have to tackle if we want to make real-time rendering tractable is that the considerations of high performance on the specific hardware we'd like to utilize will end up affecting our software architecture. And we have to not be blind to how these hardware-specific considerations affect us. So this is the part where I say, here's what I would say to any given graphics programmer you need to know about GPUs. Again, I wouldn't be surprised if we have some people who are GPU experts listening in, and they probably know significantly more than I'm going to cover, but this is the bare minimum. If you didn't know about GPUs before today, this is what I want you to know. First, that your GPU in your computer is going to run asynchronously from your CPU. And second, it is first and foremost a throughput processor. And each of these high-level statements about a GPU is going to have consequences for how we have to build rendering software. So if we look at the first one, the GPU is going to run asynchronously from the CPU in a computer. And also, if it is a desktop computer with a discrete GPU, that GPU is also likely to have its own memory. It's a non-unified memory architecture. And furthermore, we typically have to talk to GPU graphics systems through these dedicated APIs, things like Direct3D and Vulkan and Metal. And as a consequence of all these different factors, when we want to get high performance in rendering software on a GPU, we have to be prepared to use the mechanisms provided by a graphics API to organize, prepare, and communicate the parameter data of various features efficiently. So that's going to become our first constraint, is efficient communication from CPU to GPU via these APIs. And then when we look at the second point, that a GPU is first and foremost a throughput processor, what that means in practice usually is that it's going to have many threads that it uses switching between those threads to hide the long latency of memory fetches. That's in contrast to latency-oriented processors like most CPUs, where they're going to try to avoid incurring memory latency in the first place by using deep cache hierarchies and large caches. As a second factor, most GPUs, because they're running a large number of threads, do something like SIMT or SIMD execution to amortize the per-thread costs over larger batches. And I don't have time to get into all the details of the why, but both of these points have similar consequence, which is that application code running on a GPU can in many cases end up paying for code paths that were compiled in, but not executed at runtime. And you can go look up a lot of other people's talks on the details of why this is, but it's just worth understanding because this now impacts our choice of how we deal with this taxonomy of models. And while the intuition of approaching this as a class hierarchy is a good one, it's important to note that really what we're talking about in that case is that taxonomy is really about polymorphism. And as compiler developers, we know that there are multiple ways we can implement polymorphism. So on one extreme, we know that we can implement polymorphism with full dynamic dispatch, full function call indirection. So that would be what we get if we implement something as a base class in C++ and a derived class that overrides some virtual function and then make a call to it. But on the other extreme, we can also implement polymorphism via static specialization, whether that's via templates or preprocessor use. We can write the code so that we have, say, in this case, completely distinct implementations of different light source types versus the class hierarchy on the far left. And then we use a preprocessor directive just to statically switch between them. Right? In this case, we are not doing any actual dispatch. Okay. We will probably need to, oh, good. Thank you. Can we mute whoever that is, please? Thank you. All right. And as a third case here, between these two extremes, because these are not the only two ways of implementing polymorphic dispatch, we also have the case of what would be referred to as a tagged union approach, or sometimes in the graphics community, this gets called an uber kernel approach, in which we might implement a single type that has a tag to be able to discriminate between different types, plus a union or similar structure to hold a payload of type-dependent data, and then we use something like a switch statement to dispatch between them at runtime. So we have kind of a spectrum of different ways we can implement polymorphic dispatch. And when we look at our performance considerations on GPUs, what we find is that the dynamic indirect case on the far left often would introduce too much overhead on current GPUs to be something worth considering. And in fact, if you're talking about running on most current graphics APIs, it just isn't even supported. This isn't something your compiler could take advantage of, even if you wanted to. So graphics developers doing real-time graphics primarily use these other two techniques. Sometimes they write this tagged union uber kernel approach, but the conventional performance wisdom that people have shared in the real-time graphics community and in the GPU community is kind of that when in doubt, specialize your code completely. And that way you're sure you're never paying for code paths you didn't mean to include. Right? So this has significant consequences for how people architect their software. And so that's what we want to talk about next. How do developers typically implement their renderers today, given all these considerations, given the problem domain and given the GPU performance considerations? So if we look at a typical real-time graphics developer or a typical code base today, what you're going to see is CPU code primarily written in C++, and then GPU code that's written in a language called HLSL. Now, HLSL is a shading language that was introduced in about 2002, at which point it was a subset of C circa 1989. So what we will see in the next several slides is that developers make extensive use of C preprocessor techniques to be able to build abstractions in this language, HLSL. So if we go back to our big picture of real-time rendering, we're going to cover a couple of these bullets in terms of how they intersect current practice with something like the HLSL language. So our first item of building a large and extensible library of shader code with many different features, let's explore that by looking at an implementation of a single feature. So we're going to have a metal material used to render this object on the right, and we've got some hypothetical code on the left written in HLSL. And the important thing to note here is that pretty much every feature implementation that we're going to have in a renderer is going to have a few things in common. It's going to have some number of parameters, again, that need to be communicated from CPU to GPU to describe some object in a scene. It has some number of types that it uses as part of its implementation. And then obviously it's going to have some number of functions that implement the actual operations that are part of that feature. So when we talk about something like a material, there are typically going to be two fundamental operations that every material implementation needs to support. The first of those is going to be some sort of step to sample the properties of that material at a point on the surface. An object might have spatial variation in roughness or color, and we need an operation that, given a point on the surface, samples those material properties at that point and returns some representation of that point. Now, in the graphics community, we have a name for this thing. We call them a BRDF, or bidirectional reflectance distribution function. It's a really fancy term, but really you can think of this just as a closure, and it closes over some amount of parameter data. Different materials have different closures that need to close over different amounts of data. And so our metal material has its type that it uses to represent this BRDF, but different materials might have their own types. And what this closure represents is the ability to evaluate the reflectance of this surface for a single light source and a single direction to a camera or eye. So given a direction to a light and given a direction to the camera, we can determine how much light this surface reflects along this path. And if we add up those contributions amongst all the light sources in a scene, we can eventually derive the color that a person or a camera sees when it looks at that point on that object. Now, having broken down this very simple material implementation on the left here, it's worth noting a few properties. First is that there were these three requirements we had of a material implementation. It needed this sampling operation that returned a BRDF, and it needed a way to evaluate that BRDF. But in this description in plain HLSL, those requirements are implicit. They were things I said verbally that don't appear explicitly in the code. They're unchecked by our compiler. A second thing to observe is that we declared the parameters of our feature implementation globally. Like, the language forces us to use the global scope. for these. And what's more, I said earlier in our consideration of GPU performance that we needed to organize these for efficient communication, and dumping things in the global scope is not necessarily organizing them. And so you might ask, what are we supposed to do? Well, the answer is we start to manually annotate these. So what performance-oriented developers do is they take those parameters and they start adding these annotations onto them to explicitly map their parameters to the API provided binding constructs or parameter passing mechanisms. And so in this case, these is effectively a register assignment problem that you, the programmer, do. So here we have some annotations added onto our parameters, but it turns out these annotations are specific to D3D12. So we're going to need to write some more if we want this to also work on Vulkan. And so what we can end up with is parameters in the global scope manually annotated for each API in order to get efficient communication. Phew. At least we're now at the point where maybe this feature implementation will work. And of course, we want to have many different feature implementations in our renderer. So we're going to do this work over and over again for different implementations, whether it's cloth, glass, metal, and so forth. And it's worth again noting at this point that the approach taken in the language means that we're using the global scope, which means we can really only modularize our features at things like file granularity. We can't really scope them any more tightly than that. All right. Jumping all the way to the last of our big picture rendering steps, because composing the scene is not typically something that affects the shading language very much. The last step here is that we wanted to pick a program and be able to combine it with the relevant objects and features and invoke it. But we also know, again, going back to our performance considerations, that there's a missing step in how I've described it here, which is that we also need to specialize that program for performance. We want to strip out anything that we don't need and make sure that we generate code that only includes the feature implementations that are relevant to this operation. Often that'll be, what is the camera looking at? I only want to shade those things. I only want to include that code. So the way that this is typically solved is, again, with more preprocessor use. So on the left of this slide, we have our library of different material features we talked about. And on the right, we have a surface shader now, again, written in HLSL. And broadly, this surface shader on the right proceeds in two big steps that match how we talked about our material implementation before. In the first step, depending on the material that we want to choose, it's going to do that sampling operation at a given position, compute the BRDF for the appropriate material. And then at the bottom, in a loop, it's going to loop over light sources or samples of light sources, and it's going to sum up contributions of reflected light for each of those light sources. And we can see that in each of these two big pieces of the code, the preprocessor is being used to select between our different material implementations on the left. So the effect is that if the application does a little bit of preprocessor work ahead of time, sets up a define, includes the right file, we can get statically specialized output. In this case, we've stripped out all but the material implementations on the left, and we have just the one that we actually care about, and we've stripped out the code on the right to only have the code we care about. And so we can hope that we are not paying for those code paths we didn't intend, and we can hope that only the parameters we cared about are in scope. So what we're seeing here is a recurring pattern that the preprocessor is being used as a solution to many different problems at once. It's the answer to modularity, it's the answer to polymorphism, and it's the answer to specialization. And that works to a point, but we also know that there are limitations to pure preprocessor-based programming models. And again, we've talked about some earlier, but in the particular case of the surface shader on the right, it's important to note how this impacts modularity and flexibility. So by having to explicitly enumerate all the different material types at each one of these use sites, we make it so that adding more materials to our system requires manually annotating all the places that we're iterating over or switching between these materials. Similarly, we are binding ourselves statically to the decision to statically specialize. We are using the preprocessor, which means we will always statically specialize, which is often desirable, but static specialization involves trade-offs. It is conventional wisdom, but it is not good to pretend like it has no trade-offs. And in particular, in the real-time graphics community, we have this thing that gets called a bunch of different names, but I often refer to it as the shader combinatorics problem, which really arises when you have shader programs that want to work across a large cross-product space of features. I want this shader to work with different geometry types and different material types and different light types. And so for each combination of features across those different points in the space, I need to compile, preprocess and compile a unique variant of this program that only works with that subset of features. And what we find in practice is that real-time graphics developers often end up dealing with thousands of compiled variants. So for example, the game Destiny from Bungie shipped with 90,000 distinct shader variants for vertex and fragment shaders. And shipping that many unique binary kernels for your rendering operations is something that affects build iteration times for artists and developers. It affects download sizes for games. It affects load times for levels. And what's more, this whole idea of rampant specialization that leads to the shader combinatorics problem is something that's been baked into the software architecture we just talked about on the previous slides. It's something that the tool chains for major game engines just treat as a fundamental that they have to accept. And looking forward to the future of GPUs, other kinds of rendering, it turns out that static specialization not only causes all these problems, but it also isn't always the best option for performance. We've kind of walked ourselves into a corner where we only have one way of doing things, and now we pay a lot of pain for it without always getting an upside. So this is a good point to segue over to what we did on the Slang Project. So at the highest level, the Slang Project is a platform we had built at Nvidia Research that was meant to enable us to do innovation in real-time graphics programming models. Over time, it evolved into what it is today, which is a language and compiler that extends HLSL. The Slang Project is being used in Nvidia products and infrastructure. I will talk about those more later in the presentation. And it is also open source on GitHub. And when I say open source, I mean we do our active development on the GitHub repository with this URL. So the NVIDIA products and infrastructure that use Slang are using the code from this place. This is where I spend most of my days, is on that GitHub. When we started the project, we had a few key goals in mind. And you'd be unsurprised, given what we've just talked about in terms of current graphics programming models. One of our biggest goals was to enable developers to have a more clean and more modular development practice when they build the kind of large real-time rendering code bases that we often build at NVIDIA. A next priority was that we needed this system to be easy to adopt for current developers. We just knew that they already had existing investments in shader code, and we wanted to make sure they could bring it to a new system. And finally, when I talked about the shader combinatorics problem, we recognized that there was no clear path forward as an industry on this problem, and that finding such a path was going to have a component that the language and compiler needed to play, given the rampant preprocessor use. So each of these key goals then informed our choices in implementing the system. So I'm going to go through these briefly. So when we talk about clean and modular development, one of our key choices on the project was that rather than invent new language design ideas or kind of come up with whatever we felt like, we focused on learning from existing modern general purpose languages, things like Swift and Rust, and whenever possible, we decided to adopt mechanisms from those languages rather than invent our own. But at the same time, we knew that graphics is an interesting domain. Real-time graphics has strong performance demands, and so we had to be careful about what mechanisms we selected and how we implemented those in our compiler, and make sure we were always focused on addressing the specific challenges faced by real-time graphics developers. And now when we talk about ease of adoption for developers, well, the most critical choice we had to make there is that we decided to extend HLSL rather than build an entirely new language. And this decision was made because developers are already largely using HLSL, and coming up with a completely separate language would require them to port a lot of code on day one. Similarly, the desire to have easy adoption also pushed us to architect the whole system to be able to support a large number of target platforms and graphics APIs. And finally, on this point about the shader combinatorics problem, we see this as a long-term push that the entire graphics industry needs to work on. It is not just a language or just a compiler problem, but we knew that in order for the industry to get out of this hole, we needed to help developers reduce their reliance on the preprocessor, and that for our part, as a front-end compiler, we needed to take separate compilations seriously in how we architected things. All right. So at this point, I want to talk a little bit about sort of the mechanisms and features of the Slang language. And I went ahead and surveyed our current users to get a sense of what things we added they value most. And this is kind of the list they put together, but I don't really have time to talk about every single thing in it. And a lot of these are fairly conventional. Those of you who do know something like Rust or Swift can probably recognize a lot of things on here that are already in your general purpose language of choice. So what I want to actually highlight is a difference in philosophy between how we approach Slang and how HLSL encourages developers to think. So if we look at the old philosophy of traditional HLSL code, there's this mentality that a feature implementation is fundamentally a file, which means in practice, it is a loose collection of global declarations of those parameters, types, and functions. And really all we are changing at the most basic level when we talk about Slang's approach is that we want to allow a world where a feature implementation is a type. And that means it still contains parameters, types, and functions, but it is now something that can be named and provides a scope to its contents. And so this allows the developer to have a different unit of modularity than whole files. And there are specific features we had to add in the Slang system that are really there to enable this kind of type-based modularity for developers. And I'm going to cover 2 of these today, and that's pretty much all we're going to be able to talk about as far as concrete language features. So the first of these is what we call parameter blocks. And I hope everybody still remembers this per API parameter annotation mess that I showed before, where a performance-oriented HLSL programmer is adding these 2 kinds of annotation to their global scope shader parameters in order to get them efficiently communicated on a per API basis. So in the Slang system, we're saying we want to be able to support more platforms, and we also want to be able to support this type-oriented way of modularizing features. And so first off, we allow the parameters of a feature implementation to be scoped inside of an ordinary struct type. Nothing too magical there. And then we have an explicit language construct now. It's a parameter block of T using angle bracket parameterized type syntax here that allows the programmer to explicitly say, hey, compiler, I would like you to take this type that contains these parameters, and I would like you to organize it using the parameter binding mechanism of the underlying API. Whatever my compilation target is, use the thing that is most efficient there. If you are on Vulkan, use their descriptor set and binding system. If you are on D3D12, use the descriptor table system, etc., etc. Different APIs will have different mechanisms, but in this case, we're abstracting over them, and it turns out that our compiler can generate code equivalent to that on the right-hand side without all this manual annotation, because it kind of turns out that computers are very good at starting at the number 0 and counting up. And so this is kind of our philosophical approach here was we wanted to make the clean code and the fast code the same thing, rather than have developers try to write clean code and then have to spend extra time adding annotations to it when they want it to go fast later on. Turning our attention to the other big picture language feature that we added in Slang, it's interfaces and generics. And I think a lot of you are going to have experience with a programming language in the general purpose space that has similar features, but I'm going to go over these at a high level just in case. The obvious statement here is that interfaces exist to make the requirements of certain kinds of features explicit. So on the left-hand side of the slide here, we have examples of interfaces for a real-time rendering system that follows the kind of taxonomy I've been using in this slide deck. We have an interface for materials at the top, and in particular, this material interface has 2 requirements. Every material needs to provide a BRDF type and a sampling operation, and that BRDF type needs to support another interface that includes the evaluation operation. And if you use these other languages, if you use Rust and you know what traits are, if you use Swift and you know what protocols are, or if you're somehow a Haskell programmer who stumbled in here and you know type classes, you know where all of this comes from and you're not surprised. And if you haven't used any of those languages, pick one and learn it. They're all great. And now that we have explicit codified interfaces in the language, now when a type declares a conformance to that interface, here we have our metal material saying, hey, I implement the material interface. The compiler can check that. It can look at the requirements in the interface and check that the type provides matching implementations. It provides a type named BRDF. It provides a sampleout operation with the correct signature. And what's more, that BRDF type implements the interface it says it does. And so now we have some assurances from the compiler that our feature implementations conform to the contract that was previously just verbal in our HLSL examples. The next step down this road, obviously, is to have generics. Generic functions, like the one on the left here, allow us to abstract over these different implementations of a feature. So here we have our surface shader example again, but in this case, it's able to abstract over any type M that implements our material interface. And within the body of this function, it can use the operations and types provided by that interface, but the compiler can statically check that it doesn't use any operations or types not provided by the interface. And then at compilation time, if the application tells the compiler what type to use for M statically, the compiler can generate fully specialized output with comparable performance to those preprocessor-based techniques they might have used in plain HLSL. So we have a much better organization of the program and much better static checking, but we have ultimately the same runtime performance. But that's actually not all. Static specialization isn't the only option. And we're going to talk about that a little more later. But now, finally, having covered the domain, the specifics of what's in Slang, I'm ready to start talking about what I actually promised to talk about at the very start of this talk, which is the journey we took from research to production with the Slang system. So on the personal side, as far as how I ended up on this project, I've always loved video games and programming languages, and so ending up in computer graphics was kind of a natural fit. And when I got into the PhD program at Stanford, I got really lucky to be pulled into some of the original work in what we call like the GPU space, GPU compute. And even though I was working on programming models on GPUs, I was always wanting to use them to do graphics. And what I found myself doing was kind of repeating a cycle. I would find myself working on a programming model or a compiler, and I would get really excited about the prospect of applying it to rendering problems. And then I'd come around and start doing a rendering problem and implementing it in one of the programming models or compilers that I'd worked with. And I'd get frustrated because the programming model did not have all the things I needed to get the job done the way I wanted to. And so I'd come back to the top of that cycle. And so really for me, like the process of finding this research topic and getting into this space was about turning my personal frustration at the tools I tried to use to do real-time rendering into a research topic. And I'd actually claim that the real-time and GPU graphics space is a surprisingly good frustration generator. There's a really high performance bar, and there's all these heavily competing hardware companies trying to innovate and pass each other constantly. And the result ends up being a space of hardware and features and APIs that are full of caveats and rough edges and special cases. Every time you think you understand the rules, some new idea comes out that completely breaks them. And a secondary process that's been going on in the real-time graphics industry for many years now is that the barrier to entry keeps getting higher. And when I was an undergrad, I learned computer graphics in OpenGL, and that was the same thing John Carmack was using to ship games around the same time. But now with things like Vulkan, the disconnect between what is easy to learn as a student or a hobbyist and what is used to ship the latest games is getting further and further. And so the challenges of just wrangling this hardware at all have gotten more and more significant over the years. And so this is something where kind of like what I call the programming language brain inside of me really wants to square that circle. It looks at this problem space of real-time rendering and says, it just shouldn't have to be this complicated. We shouldn't need all these complicated corner cases and so on in our programming models. And really, I just kept working on finding ways to phrase that as a research question, not a request question. Sorry for the typo in the slides. And we've actually learned a lot. So we've spent a lot of time figuring out how to phrase these kinds of challenges and frustrations with GPU programming models as research problems and published a lot of papers in this space. We've worked on multiple research systems, my collaborators and I, and addressed different parts of the problem domain. And what we did after each of our major publications or each of our major systems was we went around and talked to game developers and gathered feedback on what they thought of what we built. And there was a common theme, time after time. They would say, that is a neat system. I would love to try it out sometime, but it's just too risky for me to abandon my investment in these tens of thousands of lines of HLSL and try out your little research language. I believe you that it will actually provide some of these benefits, but I can't take that risk. I've got games to ship. And so what we realized was that we were spending a lot of time learning things as researchers, but we weren't finding a way to have that impact on the industry. People said, yes, this is great. We like it. We just can't use it. And so the Slang Project represented a really big shift in our thinking, even as researchers. We realized that we had to treat real-world adoption as our primary goal and take the compatibility, build a compiler that is compatible with the code they already have became this hard constraint. And so we actually rephrased our research question. We no longer asked, can you build something better along axis X, Y, or Z? We said, what are the minimum number of things? What are the necessary and sufficient things to add to a current language that could make it solve these same problems, right? Instead of inventing new things, we tried to say, what's the least we can get away with? And that led us to this philosophy of seeking out existing, well understood language mechanisms, which kind of feels wrong as a researcher. We're supposed to pursue novelty, but in this case, we were trying to be as not novel as we could get away with, right? And this idea of pushing for adoption is also part of why we started the project open source, kept it open source, and keep trying to push for it to be cross-vendor. I mean, I work at Nvidia, but I want to say, like, Slang is not something that is an Nvidia-only shading language, and we never intended it that way. So to get into some details of how this has worked so far, trying to build this system, I want to note that solving real problems instead of just research problems can require being willing to just get messy. I think the research community has a tendency to love simple answers to hard problems and has a hard time accepting that sometimes real problems in the real world have solutions that are complicated or messy. So to make a concrete example of this, we needed to support a bunch of different graphics APIs and a bunch of different compilation targets. And I think the clean answer that a lot of people would have pushed toward would have been to bottleneck through some existing system, whether that's the SpearV IR provided by Vulkan, LLVM IR, something like MLIR. But from our perspective, that would have required dropping some of the targets we needed to support based on what the particular bottleneck we chose supported, or reducing all of the systems to some kind of lowest common denominator, reducing everything to the capabilities of SpearV and then cross-compiling to everything else. And so in practice, we actually opted for the messy answer that worked at the time we started the project. We did a custom IR and we used source-to-source translation, which sounds like a naive implementation choice, but it was actually just us facing the reality of needing to support a huge number of platforms that weren't commonly supported by these sort of one-size-fits-all IRs at the time. So this is an example of being willing to do the not pure, not clean thing just to get the results done. And so that kind of thinking is what helped us get our foot in the door with our first customer at NVIDIA, which was our colleagues also in NVIDIA research, but the people doing actual rendering research. And so a lot of the images I've shown you so far are coming from renderers built by that team. So the real-time rendering researchers at NVIDIA were our first customers for the Slang system, the first users we could get on the hook. And at the time we started engaging with them, they had their own framework they were using. This was far enough back in time that they were using HLSL and GLSL as their GPU languages and trying to target the D3D11 and OpenGL APIs. The world has changed a lot since then, and we've had to migrate with them. What we found when we started engaging with the people building this framework for the researchers was that their biggest priorities weren't the same as what our research interests were. They came to us and said, hey, we actually just need something for cross-API code sharing. We need this portability piece, and we actually need a decent parameter reflection API. And none of the other compilers we've been working with do reflection right. So they came to us requesting those pieces, which weren't really aligned with our research goals at the time. They also came to us and wanted an exit strategy. If we failed to deliver, they wanted to be able to go back to the way they were doing things before. And so a consequence of this was that in order to get our foot in the door, get them signed up as users, and start building credibility, we actually had to implement a lot of special case code to meet their needs. There are some very old versions of the Slang system where we actually supported both HLSL and GLSL variants of our language just to be able to meet their needs as they migrated their code base forward. Another observation from that time integrating with the real-time research team is, I should note that getting our foot in the door was worth it. Sorry, I should start at that. Because having users is really important as a systems researcher. I think despite having worked in this space for many years prior to the Slang system, we learned a lot more once we had people using our system who had deliverables that weren't our research paper, right? They had their own papers they needed to get done on time. And so having those demanding users giving us feedback on everything we implemented and invented for them was great. But getting the most out of that relationship has been something we have to invest in. We have to engage them early. We have to treat them as co-designers for features, not just throw things over the wall. And the reality is that the first thing we come up with is unlikely to be the best in practice once we get the users in the loop. So another piece there that's related to that is needing to compromise with users. And that was something that was a little hard for us to swallow, which is that a feature that gets used is always better than one that gets ignored, even if you don't like the implementation, you don't like the syntax or whatever. And it's important to realize as people building tools that once you have users on the hook, you can start a process of iterative co-design, right? So sometimes we did have to kind of hold our nose and deal with syntax or semantics or implementation choices that had a lot of compromises necessary to get that first user to try it out. And often after that, we could iterate and get the user and the system into a state we were happier with and that was better aligned with our long-term goals. But often we found that we had to just let users learn by experience. Us coming in and saying, we're the people who know programming languages, just trust us, doesn't always work. They need to learn for themselves what actually works for their code base. A concrete example of where we kind of had to make these compromises, which wasn't a big one, but I want to talk about that in the original Slang system that we shipped to users and tried to get them to use, we made the syntax for generics very explicit. We always used interfaces in particular as type constraints. We always had this angle bracket syntax. We always had the interfaces appearing as type constraints. And nearly the first thing that our users wanted to do was start writing what looked like object-oriented code using this thing. Because it turns out graphics developers use a lot of C++. They often think in object-oriented terms. So they immediately started trying to write things that to us didn't make sense. We were saying, like, no, we don't actually want you to use it that way. We want you to think in terms of generics, not some kind of dynamic dispatch thing like you think of in Java or C#. We ended up having to compromise and just implement this for them because this was what their fingers typed out, whether they meant to or not. And some of them were traumatized enough by C++ templates, they just didn't like having angle brackets all over the place. A consequence of this, of course, is that as soon as we gave them this syntax, they started asking for implementation inheritance, and slowly the language has been migrating toward more and more object-oriented ways of approaching the problem, instead of maybe a more purist approach like we started. And I don't think of this as an unhealthy trend, but it was something we really wouldn't have run into without spending time working with our users and hearing what they actually wanted. So our experience with the real-time rendering team then led to us having a second adopter inside of Nvidia, which is the Omniverse platform. So broadly, Omniverse is a real-time 3D content collaboration system. You might want to think of it as Google Docs, but for 3D scenes. And it is a pretty big production effort. It is no longer just within Nvidia research at this point. And that's really where it came to the fore that building relationships with our users is really important. They have things they need to ship. They're on the front lines of real-time graphics development in our case, and they know the domain better, right? I've been working in real-time rendering for a bunch of years, but at the end of the day, I spent most of that time writing tools instead of renderers, and they all know their challenges and problems better than I do. And so it was really important for us to spend a lot of time with the users and getting to understand their specific code bases and challenges. And we actually had times where people from the compiler team would spend a little time on those dev teams working with them for a few sprints. Like they were integrating something new from us, having us in the loop writing the shader code right next to them was really important. And building that relationship is also something that I think has been really important because sometimes we needed to know when not to compromise. And having users who trust you and know that you'll listen to them is important for when you want to say, no, I'm not listening in this case. We maybe actually do know better. And so to get into a concrete example of that, I want to address something that might actually be like an elephant in the room that people are already waiting to chime in with as a question, which is why not just do C++? Because real-time graphics developers write a lot of C++. And as we onboard new users for Slang, one of the first things many of them ask is, why do we have these generics instead of templates? I write templates all day in C++. Can't I just have those? This is something where we believed strongly in our choice. This was one of the first things we decided on when we started the language design project process, and it is something we stood by. And it's also something that I think paid off and not in the way that users necessarily expected coming in. So part of how that came about is it turns out that ray tracing is a thing. But when we started the Slang project, most real-time graphics was rasterization based. The reality is that most of our current users spend all their time tracing rays. They're building ray-traced renderers primarily. And that was a huge shift in the kinds of workloads that our compiler was expected to run. It doesn't change the language they wanted to write it in, but it does change a lot of things about the performance characteristics. In practice, ray tracing defies most of the conventional wisdom of GPU performance that I described earlier. Most of what we understand doesn't perfectly match this world. So again, the conventional wisdom said we should always specialize, this case on the far right of our choices of polymorphic dispatch. But if we want to implement fast ray tracing systems, very often we have to build these uber kernels. So already we're moving a little bit more to the left. And again, one of our goals at the start of the project was that we knew there was this shader combinatorics problem, and we knew we needed to help the industry find a way out of it. And the fact is that finding a long-term viable solution to the shader combinatorics problem means we need some kind of separate compilation. Doesn't have to be virtual functions and classes like on the left here, but we need to start moving towards something that has modular separate compilation, like most modern languages that support dynamic dispatch do. And so we said we need a system that does not dictate one or the other of these implementation choices. And this comes back to the question of why generics and not templates. And the short version of this is generics can do things templates can't. So given this code on the left, here I'm using that fancy object-oriented syntax our users insisted we added. So while you don't see the angle brackets for the generic here, let's just pretend there's a generic type parameter for that material, because that's really how it's working under the hood. And the benefit of this approach is that the user and the application can control the code generation strategy in contrast to something like virtual functions. So given this dispatch point here, we already know that static specialization is possible in this system. We can swap out the eye material with this metal material specifically and get fully statically specialized code. But within our compiler system today, we can also simply take a list of different implementations. The application can say, here are the 3 materials that happen to be in my scene. Out of my 100 materials, these are the 3, and have us generate a switch statement for them. We can generate the tagged union type, we can generate the switch statement, and they get that Uber kernel code, again, without having to write any new code on the left. And finally, for platforms that already do support function pointers, which today is CPU and CUDA, we can also generate a dynamic function pointer based dispatch implementation from the same code on the left. Again, anybody out there who has worked on or with the Rust or Swift languages is probably not surprised by this point, but this was something that our users didn't actually initially understand was distinct between generics and templates. So this ability to generate different kinds of code from the same input was something that we intended from the start because it is a clear way to get developers a path out of this shader combinatorics problem. We gave them an answer that they can adopt generics and interfaces today as an alternative to preprocessor-based specialization and not lose any performance. And once they're in that world, they can easily experiment with and adopt tagged union styles of dispatch in cases where it makes sense, whether that's ray tracing or deferred shading. And furthermore, once they get their code into this world, instead of a preprocessor or template world, they can be more ready for any future where hardware, driver, or API innovations allow more of a shift toward dynamic dispatch or true separate compilation. So this was kind of an attempt to help developers get their code into a little bit more of a future-proof or forward portable, at least, state. And it turns out that once we added this functionality to our compiler, this ended up almost immediately having payoff in the real-time path tracing research that the real-time research graphics team at Nvidia has been doing. So all of the images on the slide here are generated in a real-time path tracer that my colleagues at Nvidia have developed. They talked about this recently at both the GDC and GTC conferences. So if you go look up this talk title, you'll be able to find their discussion of the renderer itself. But also part of what they talk about in those talks is how they leverage the features of the Slang language that I just talked about, these different compilation strategies to allow flexible experimentation with performance and also to compile for different scheduling strategies for ray tracing workloads. So this turned out to be something where the users are now thankful that we stood our ground and put in generics instead. So I don't know where we are on time, but it's probably a good time for me to wrap up either way. In terms of the Slang project itself, we are not done by any chance. We are continuing to evolve and extend the language and compiler in cooperation with our users. For anyone out there who's interested, we are hiring. And looking to the next year or so of horizon, we know that a big problem for us going forward is interoperability. We need to focus on how this language is going to interoperate with C++ code bases, as well as with what's called HLSL 2021. So while we went off and built Slang and did generics, it turns out that that was us forking the HLSL language design, and Microsoft has subsequently made a version of HLSL that has template support and some more C++ features. So these languages are now kind of on divergent evolution paths, and that means that it's important for us to figure out a strategy for how they play nice together. On the research front, we are still using this platform actively to do computer graphics programming model research, and on that front, we're very interested in heterogeneity, the question of how do we provide single source file programming models for real-time graphics in much the same way people often use single source file programming models for GPU compute. So just to kind of summarize everything, bring it all back together, this process of taking Slang and bringing it from a research project through to production has been a really long-term balancing act. It started with a conscious decision to prioritize adoption and real-world impact over publication goals, and that started at the inception of it. And I think that's really important for researchers who want to see the thing they're building get adoption. It was clear to us that building relationships with our users over time is actually something that made both the research and the system stronger. And so we firmly believe that the compromises we had to make along the way to get our foot in the door and get some users on the hook was really important for us. But at the same time, it's been really important to know when not to compromise. We've been working in this space for many years, and it's important for researchers to know when to respect the insight and the expertise that got you started on a roadmap to begin with. For example, for us, that was sticking to our guns and saying generics are the right long-term solution here, and knowing when to stand up for those ideas that are hard-fought realizations or learnings is important. All right, I don't know where we are on time, but thank you all so much for tuning in today. And yeah, I will mute for a second and we can see if there are questions.
Thank you, Tess. That was great. I'm glad we recorded it because I'm sure I'll be going back to it. We can start with the questions now. So folks can either just ask the question or type it into the chat box, and I'm happy to read it out. And yeah, Michelle, you can go.
Hi, Tess. Can you talk a little bit more about these generics versus templates? So how is it that generics are able to let you pick between these different code generation strategies?
Yeah, at the most basic level, you can definitely look at how things like Swift and Rust implement their generics in particular, but the key observation there is that we have the interfaces. Let me see if I can actually back up through the slides and get to that. Really what makes it possible, we're never going to be able to scan through all that in time. What makes it possible to do dynamic dispatch implementations for things like generics is having the interface part. So actually I can just leave it on this slide. By constraining a type parameter to one of those interfaces and just the operations in it, it's possible to generate what we actually kind of follow the terminology of Swift and refer to it as like a witness table. I think Haskell people call it dictionary passing, but we can basically think of this as a case where you pass down a dispatch table that has the operations of the interface separate from the payload of the actual value and do dynamic dispatch through that. Or in our case, generate a switch statement and we're passing down a tag. But by codifying the representation of conformance is really the key. And C++ templates don't have that unless you add concepts on it. And concepts, while they do form a type system over template type parameters, they don't necessarily have the design characteristics that make them especially useful for dynamic dispatch, if that makes any sense.
Yeah, I think that makes sense. You said something about it's also implemented in Swift. Is that a good place to go read more about this? Or
I think if you are interested in generics and how they support both specialization and dynamic dispatch, looking into Swift and or Rust is a good thing. I think Rust is convenient to look at in that it is an explicit choice that the programmer can make textually in the language. So a Rust trait can be used either for sort of specialization, I think they call it monomorphization in their case, or for dynamic dispatch. And there's distinct syntax in Rust so that you can know which of those cases you're on, but they both use the same trait construct. So that might be a great place to look, but also the Swift compiler gets into the point that the compiler can make choices here or can have choices mediated by profile information or application information about when to specialize or when to generate dynamic dispatch. And so Slang is kind of operating in that same space.
okay, cool. Thank you.
No problem. Looks like we had another hand raised. Go ahead and chime in.
Yeah.
Hey, can you guys hear me fine? Cool. Yeah, I was wondering if does Slang transpile to HLSL, or did you guys also do some work in like in the compiler backend, like implementing new optimizations or things like that?
Yeah, so the answer to the first part of that is that we are still primarily a transpiler. Again, it just turned out to be the right trade-off in terms of implementation effort versus coverage of platforms. We know that our end-to-end compile times could be improved by generating things like SpearV or DXIL directly. And indeed, the internal IR we use, so we generate our internal IR. We do all the implementation stuff related to generics and a lot of specialization work on that. We do high-level optimizations, not necessarily low-level optimizations, and then we emit source code. So we know that we could more directly target SpearV from our IR. They're on comparable abstraction levels. It would be possible for somebody to write a backend directly from our IR to something like DXIL. It's just not something where we see that the return on that would be worth the investment. So we currently just generate high-level HLSL and then feed that through another compiler downstream. That's an implementation detail rather than a fundamental choice, but yeah, we focus on high-level optimization and currently allow other compilers to do the low-level code gen work. But that's something we would like to do less of over time.
Okay, thank you.
Will, you can go next.
Yeah, thanks for giving this talk. This is really exciting to learn about, learn more of like the details about Slang. I was wondering specifically for kind of like when you're finding the parameter blocks to the registers for DirectX or like Vulkan, if you have a lot of parameter blocks that are coming in from different materials, how do you handle like conflicts or like collisions there when you're doing the mapping? Like, does everything have to wait till like the final runtime when you know like what parameter blocks you're going to need at that time to like kind of reduce everything down? Or can you do some pre-compilation? Because it seems like it might need to work with some conflicts or stuff for those mappings.
Yeah.
I was curious about that.
So the answer there is maybe anticlimactic, but it's really something where the internal structure of a type, just like if you were building a C compiler, right? Like given a type, you can compute the relative offset of each of the fields in that type from the start of it. Given a type like metal material on the left here, we can compute relative offsets in terms of bindings or registers or whatever the particular downstream API uses as its abstraction for that type. So each of the fields knows its relative offsets, and if it is an aggregate type, it knows the structure recursively of all the recursive offsets under it. And then it's really only at the top level when we have the entry point to a shader and the programmer declares the parameters of that entry point that sort of anchors that type at a fixed offset, right? Like just like a C struct has relative offsets for the fields, but never an absolute offset in memory. Like to get an actual pointer, you have to start from somewhere that's anchored. And so it's sort of the same story that we can compute per type relative offsets. And then when we finally have a root shader parameter of an entry point function, that sets up the absolute offsets. And so we avoid conflicts the same way in terms of assignment of location, the same way that in C you can have a struct that has two fields of type X and they won't end up conflicting with each other because the relative offsets are the same for both instances of X, but obviously they're at different memory locations. So if you think of it that way, I think most of the intuition maps out, and I can give more detailed explanations, but I hope that intuition holds.
Yeah, got it. Thanks.
So Tess, I had a question. So how do you measure the success, or what are your performance metrics for success of Slang? Is it performance gained, right? When somebody makes that transition of a particular, say, rendering system from HLSL to HLSL with the Slang extensions? Or is it number of bugs found because of type errors that could not be found with the earlier method, and now with the use of Slang, you could find all these type-based, issues with types? Or is it about the productivity measured in by some metric?
I think, speaking for me personally, whenever I've done research, it's that last one. Like my drive whenever I work on programming models, I think of myself primarily as a designer, which means I care about the users of the system being happy that they're using it, like that they can get the work they want done and that they're happier using the system than not using it. And I think for me, that has been a challenge whenever I've had to do research, because that's very hard to be empirical about. Like you said, you can try to do sort of user studies about how productive people are, but they're very rarely great as far as giving you hard data. And so honestly, that's something that we've had to be careful about how we evaluate it. We usually evaluate via just testimonials from users, experience, and often our evaluation consists of they chose to adopt all these things. Here's some examples of how they cleaned up their code and it didn't get any slower, or it got this much faster, but it's usually not many percent faster. Usually the performance gains of structuring your code better are minimal. And so it's really productivity gains that are hard to measure. So I don't know if that's a satisfying answer, because to me, that was the least satisfying part of doing research in general, was that there's no way to really be empirical about certain aspects of design, even though people can intuitively say, yes, the code on the left of this slide is obviously better than the code on the right. It's really hard to quantify that.
Right, and also selling it to customers, right? Like to be able to go and tell them that, hey, do this. Okay, this seems like a good idea, but sometimes it's easier to sell when you have some, you can show them some numbers and say, this is the improve. So usually this is the performance improvement that you're going to get with this adoption.
Oh yeah, strong agree. Like, I mean, having worked mostly at hardware companies, I am very familiar with that mindset of like, performance is the metric. And if you can show us performance went up, it's good. If you can't show us performance went up, what was the point? And that has been, again, like that is a challenge. And I think our biggest thing is having a better architecture to your software can help you achieve higher performance. And those GDC and GTC talks about the real-time path tracing research, I think are a compelling example of that, is that the ability to rapidly iterate on their design by having less cruft in the code and more structure was actually part of how they achieved the performance results. So it wasn't like this language feature made it X% faster, but being able to rapidly alter design choices because the architecture was much more clear and compiler enforced was a value, and helped the researchers make all the smart choices that optimize their code.
Right, makes sense. I had one more question, if we have no others from the group here. Okay, I guess I can ask that while we're waiting. So why is there so much resistance for another GPU programming language? I mean, we have so many in the CPU, right? Like C++ has been around for a long time, but that did not stop Rust and Swift and other system programming languages to come up. And, there's, again, you have legacy code bases and all that. But this argument I keep hearing, especially with HLSL, is that, oh, we have all this IP, we have all these shaders, these legacy shaders, and there is this resistance to adopt something new because then, unless it's compatible with that, we wouldn't want to do it. So and given that the situation is kind of bad in, in the HLSL world, especially, some of the stuff that you spoke about, why is this resistance?
Oh, that's a complicated question about the sort of the state of the industry and everything. It's worth remembering that until pretty recently, we didn't have DXIL or SpearV. We didn't have well-defined sort of virtual ISA level interfaces to particular graphics APIs. So the reality was each graphics API had its source language, and there was no other way to really target it. And so SpearV, and to a lesser extent DXIL, start to open the door to more languages being possible on top of these platforms. But honestly, that's part of the sticking point, is that we don't have pervasive enough like virtual ISA interfaces to different graphics platforms the way we do in the CPU space. That, they're not even virtual ISAs in most of those cases. But that is one of the big sticking points, is that the actual work of developing a compiler on top of these is more significant, and people tend to, I think there's a bit of a tragedy of the commons thing. If we can all kind of collectively as an industry agree we wish there was something better, and then what happens is each game studio maintains its own cobbled together handwritten HLSL translator, or they just use DXC, and the cost of building something new is high. Having worked on a compiler in this space for a long time, the sheer number of platforms and the opacity of some of it, it's not an easy task. And the APIs don't make the task easier. SpearV is a huge step forward and makes Vulkan a much easier platform to compile for than almost any other. And that really needs to happen across the board to make more compilers and more languages kind of crop up.
Okay, makes sense. Cool. Okay. I think we did this in good time, and if there are no more questions, I'll call it an evening. Thank you so much, Tess. This talk's great, and learned so much, and and the questions that followed, and we look forward to having you back here sometime.
Yeah, thank you so much, everyone.